Alrighty. So the last topic in magnetism, before we get into electromagnetism, is Ampere's law. As it says on the slide, this is kind of like a magnetic version of Gauss's law. It's not literally a magnetic version of Gauss's law, because if you try to do Gauss's law for magnetism by doing like a flux through a closed surface, which is what I got written here. My little laser pointer is very slow. You get 0, whereas with electricity, if you looked at the flux through a closed surface, you would get something proportional to the charge inside. The reason that doesn't work for magnetism is that there's no such thing as a magnetic charge exactly. We do sometimes talk about magnetic poles, but you can't have just an isolated like North Pole sitting there by itself, even at the like level of individual particles. Magnetic fields have a dipole nature. You can't. There's no such thing basically as a be called a monopole, but magnetic monopoles do not exist. So Gauss's law is not helpful for magnetism. I kind of have that illustrated on the left as well. So you see a current flowing out of the screen. That's the circle with the dot that has the I next to it, so you know it's a current. That current produces a magnetic field, which is circular. And since the current comes out of the screen, the magnetic field direction is counterclockwise, which you can determine from right-hand rules, as previously discussed. So like if I drew a Gaussian box or something around it, you can see that the field line like enters and leaves the box multiple times. But that means that the flux due to that field line is 0. Even though I have a source of field inside, right? Like the current is what creates the field, but looking at flux through a closed surface is not going to do it. The thing that made Gauss's law so helpful was that we were calculating a dot product, and if we were clever about how we arranged things, we could make the dot product in the integral become trivial. And there is a way to get some trivial dot products with that magnetic field line, but instead of making a closed surface and calculating flux, what I want to do is draw a path. So at the bottom is what that's going to look like. I still have the same current and the same magnetic field. I know, at least in principle, the magnitude of that magnetic field, which I'm able to calculate by doing an unpleasant integral with the Biot-Savart law. Talked about that in a previous video. I didn't actually evaluate it, but can be done. So instead of making a surface, I have this path. It's not a closed three-dimensional shape. It's just making a circle. In this case, it's a circle. Now the path does have to be closed, and so frequently it'll be called a loop to emphasize that closed nature. But like if I start at the point P and I go around in a circle, following the field line the whole time, what I'm going to do is divide my path up into many tiny little pieces. So each element of a path I'm calling a ds. I probably should have put a little vector arrow over the s, and I forgot. And each time I take one of those little tiny ds steps, I'm going to do a dot product between the magnetic field and the step ds that I just took. And in this particular case, because my path perfectly follows the field line, it's very convenient. It means that the dot products are all trivial. And so for on any given step, the dot product of B and ds is just the magnitude of B, which I already know, times ds. So I have the steps for that written out starting here. Again, I'm integrating B dot ds around the whole circular path. I plugged in the formula for B for a single infinitely long current. All of the variables in the integrand there are independent of S. They don't depend on S, so in the next step I took them all out of the integral. Then I'm just integrating S around this closed path. The answer to that is going to be the circumference 2 pi r. And if you simplify that, you get mu naught times I. And I, conveniently, is the amount of current that's inside the path. So Ampere's law states, and again, this should feel very similar to Gauss, not exactly the same, but similar. It states that if you integrate B dot ds around a closed path, you get a constant mu naught, as opposed to the 1 over epsilon naught, times the enclosed current. And again, I haven't really proven that. I've only gotten to this by writing something out for a particular special case, but this result is true in general, even if the situation is more complicated than the one that I've illustrated. So that's our law. That is Ampere's law. The enclosed current thing is worth talking about a little bit. So I have a new illustration here with 4 currents. All of these currents are perpendicular to the screen. You can see 2 of them go inward and 2 of them come outward. And I've illustrated a path shaped like a kidney bean or a boomerang. The purpose here is just to show that whatever path I choose, and it is arbitrary, although like with Gauss's law, there are certain paths that are going to be useful and other ones that aren't. But the current enclosed by that path has to include I1, I3, and I4. But the directions of the currents are important. So with the direction of the path that I've drawn, counterclockwise roughly, currents I1 and I3 are both positive, current I4 is negative. And you can determine that with a variety of right-hand rule gestures. So like, again, I said the path, although it has that funny dent in it, it's basically counterclockwise. And so like, if you hold your right hand up to the screen and let your fingers circulate counterclockwise, your thumb's going to be pointing straight at your face. Your thumb represents the positive direction there. This is similar to the right-hand rule for showing the direction of the magnetic field around a current also. So like, if I imagine holding wire I1 in my hand with my thumb pointing in the direction of the current, which is towards my face, my fingers, which show the direction of the magnetic field produced by current 1, they go counterclockwise, which is the same direction as my path, and so they like align with each other in that way. That's why that current is considered positive for this path. Current 4, which goes into the screen instead, is the opposite. Okay. Let's look at a couple of examples. On the top half of the screen, I have just a thin wire, and I want to find the magnetic field at a distance r away from that wire at this point P. This is a result we already know, because again, in principle, you can use the Biot-Savart law to get this by doing a scary integral. In this case, though, the integral is super easy. The integral of B dot ds, B is constant around this loop, The dot product is always trivial because I'm going in the same direction as the field line and I'm going parallel to it. So this just becomes the integral of ds around the loop. So it's b times 2 pi r. That has to equal mu naught times the enclosed current. The enclosed current is called I. If you solve that for b, you get the b expression that we've already talked about a few times. So again, in principle, you could do that with the Biot-Savart law. Very annoying to do it that way. But if you do it with Ampere's law, it takes 10 seconds or something. So like, it's not like you have to memorize this formula. You can if you really want to, but you can use Ampere's law to find it extremely quickly. Below, instead of a thin wire, I'm imagining a wire that has a non-zero radius r, big R, for the radius of the wire. And I'm going to say that the wire has a uniform current density J, which means that across the entire cross-sectional area, across the whole face of the wire, the current density is the same. You'll see some questions where the current density is not uniform, where it's going to depend on radius. Again, really similar to a bunch of Gauss's law questions that you did where charge density depended on radius. This time it's the current density instead. But regardless, I want to know about the field inside the wire, so I'm going to make a little Amperian path or Amperian loop inside the wire. My Amperian path has a radius little r. I'm going to go around it in the same direction that the magnetic field goes, which I have illustrated. So the b dot ds side just becomes b times 2 pi r, yet again. For the enclosed current, I need to think a little bit. The way I've written it here is that I have the total current I, and I'm multiplying that by the ratio of the area enclosed by my loop versus the area of the entire wire. Obviously, I don't really need the pi's there. Pi's are going to cancel. But that's the way I've set it up. That's not the only way you can think about it. You could also say, like, it's the current density times the area contained by my loop, and then you have to write the current density as I divided by the total area, and you end up in the same place. So when you simplify that, you get the expression I have boxed at the bottom. And this again should give you some Gauss flashbacks, sort of, where if we're outside of the wire, which is basically what the top result was about, I have like a 1 over r to some power sort of thing. And if I'm on the inside, I have like little r in the numerator and big R in the denominator. It still works out to the same number of, like, you know, the units are the same. If I were to sketch a graph of it, it would look like that. I have a linear increase in the magnetic field as a function of r as I move from the center of the wire out towards the edge. And then once I reach the edge of the wire, the field starts to drop off, following a 1 over r proportionality. All right, next example. Device called a solenoid, basically a really long coil of wire. And solenoids are in many ways a magnetic equivalent of a capacitor. Capacitors are a specially arranged formation of charges that creates a uniform electric field. We use them in circuits to store energy. They have growth and decay behaviors in circuits. All of those things also apply with solenoids, except we're making a magnetic field by arranging electric currents. It still has time-varying behavior in circuits. It still stores energy in circuits. Still makes a uniform field, etc. So the circuit symbol for a solenoid is a curly Q, kind of like what I have drawn in my schematic there. Usually you don't draw that many, the little loops, but it's just a few loops. Below that, what I'm showing is a cross-section of the solenoid. So the idea is that the current is going around in these circles. At the top, the current is coming out of the screen towards you, and then it wraps down around, and then it goes into the screen at the bottom, and then behind the screen it wraps back up again. So I've drawn an array of dots on the top, an array of x's on the bottom to show those current directions. You can determine the direction of the magnetic field inside with, of course, a right-hand rule. So if I put my right hand like on that top layer of wires with the thumb pointing towards me because the current's coming that way, I can see that below the wire, the magnetic field should go to the right. And similarly, if I look at the x's on the bottom, if I point my thumb into the screen, then above that layer of wires, which again is where the inside of the solenoid is, my fingers are going to the right. So the magnetic field inside this solenoid points to the right. And again, it works out to be uniform, assuming it's infinitely long and there's no gaps between the currents, etc. All those idealizing assumptions that you might guess if you had to. So that's how you make a uniform field, with electricity, at least. I'm going to introduce a few variables here, so you can see that I've labeled the length of my solenoid with a big L. Again, ideally it would be like infinitely long, but for a non-infinite solenoid, we have a length L. The number of turns or coils or loops in the solenoid, how many times it wraps around, that is named big N. And then there's also this little n, which is the number of turns per length, or the turn density. Strictly speaking, if you were going to do this for an infinite solenoid, you'd have to talk about it in terms of the turn density, because you can't use the actual length because it's infinity. But you can see that I have the result written in both ways. So if you want to calculate the field inside, make an Amperian loop. I'm making mine rectangular, and it has a length d. When I integrate b dot ds around that path, the only part that contributes is the horizontal part inside the solenoid. The horizontal part that's outside, the dot product there is 0 because the magnetic field there is 0. For the vertical parts of the loop, the dot product is 0 because my path is perpendicular to the field. So it's just that bottom stretch that contributes anything. So the integral result is BD. And then the enclosed current is the current of a single wire, which I named I, times the number of wires. And the number of wires inside the loop is little n times d. Again, little n is number of turns per length, so I multiply that by the length d. That tells me how many. So the magnetic field of the solenoid you can write as either mu naught times little n times I, or as mu naught big N over L times I. Those are both fine. The solenoid formula is on the formula sheet. It's on the College Board formula sheet. I forget whether they do the little n version or the big N version. But one of those is on there. So you don't have to derive it from scratch if you need to use it. It's not uncommon for them to ask you to show how it comes about, but at least you know what the answer is going to be. And the last thing I want to talk about is a toroid, which is what you get when you have a regular solenoid, which is a long tube, and you just bend it into a circle. You can think of this as being like a donut shape. When you do this, the magnetic field lines also connect to each other, so the field lines are now circles. In my drawing, I've drawn it like looking down on the donut from above, and I've indicated that the current on the outer edge is coming out of the screen, and the current on the inner edge is going into the screen. If I wanted the current to flow the other way, that would reverse the magnetic field. I'm almost out of time. But with the way I've drawn it, the magnetic field is clockwise. So, yet again, I'm going to draw an Amperian loop. My loop is going to basically stay right on top of that field line the whole time. So the integral is b times the circumference of the circle. So if my loop has a radius little r, there you are. And the enclosed current is the current of a single wire I times the total number of turns in the toroid, because I've encircled all of those outcoming wires. So every single wire in the toroid I've included. So I need the big N. Solve it for B. There's your magnetic field inside the toroid. And notice, unlike the solenoid formula, this does depend on a coordinate, depends on the coordinate r, which is your distance from the center of the donut. So the magnetic field strength is not uniform. The direction obviously is not uniform. But the magnitude is not uniform either. So that's an important distinction between toroids and straight solenoids. The field is not uniform. And that is it for this video. I made it for the gong sound.